Okay, so thank you very much. First of all, let me acknowledge all the people from my group, which is the group of solar astrophysics. It's actually one of the recent groups in the Faculty of Sciences of this university. In 2012, we gathered a bunch of students. Okay, so here is a picture which is not a new one, but some of these guys have already left our observatory and they are doing their PhDs actually in Germany. There are two of them in Max Planck Institutes. So from 2012, we started to develop a branch of solar physics, which is in charge of a magnetic field. So basically, I'm going to talk about how the magnetic field shapes the behavior of the sun. And also, let me tell you that in 2016, Colombia got member of the International Astronomical Union. After many years of being not in the union, in 2016 we were again members of the Astronomical Union, and we organized the first symposium in solar physics in Cartagena, which is a very nice city on the coastline. And there were many people, nearly 250 solar physicists, and they were actually talking about different branches in solar activity, and that's how our students got in contact with some people, and now they are in different places of the world. So basically now I'm going to talk about the structure of the solar atmosphere, and also, the talk before by Dr. Shapiro already talked about a little bit about activity, but I'm gonna give you a brief sneak peek of how the sun behaves in different layers. So basically you have the inner part of the sun, which is the core, where you have all the energy being produced, and then you have the energy transporting till the surface of the sun. And then you have two layers, which is the radiative zone, well, first radiative zone and then convective zone. And then you get to the surface of the sun, which is what we call the photosphere, the sphere of light. And after that you have the atmosphere of the sun, where you have the chromosphere and the corona. And basically these are the pictures that you can get with a camera and the proper filter. So you have the photosphere, where you see the sunspots. You have the chromosphere, which is the one you see in total solar eclipses, and you have the corona, which is also seen in total solar eclipses. Actually, the name corona was given by a Spanish guy, and that means the crown of the sun, the corona. Obviously, you need certain amounts of exposure times and things like that to be able to observe those structures in every layer. The motivation of this work is basically the first one I will say is that the sun represents our best astrophysical laboratory. In the sun, you can actually prove physical processes from the inner part of the sun to the solar atmosphere, and those processes are also important for other branches in physics, like, I don't know, reconnection and plasmas and wherever. But also the sun is the most important astronomical object for our civilization, and the talk about solar variability and how the solar variability impacts air, it's quite an important one. But in this work in particular, we are trying to understand how is the complex interplay between the magnetic field and the plasma in the sun at different spatial and temporal scales. And I will show you how these scales behave in the sun. So how do we do that? How do we try to understand those things? Well, we have the theory, observations, and simulations, and if we combine the three of them, we get to unveil the behavior of the sun. And that's how we work, basically. So I'm going to give you an observational approach, better than the theoretical or the simulation one. Again, resembling what the Dr. Shapiro said, you have the solar activity, and then you have these sunspots, and they appear on the solar surface, and you see how the activity of the sun increases. That means that there are more number of sunspots on the solar disk, but also these sunspots start to move from the equator to the, from the poles through the equator, and that takes place every 11 years. And here is the surface of the sun, and this is the upper chromosphere of the sun, and you see how the sunspots are actually very bright in upper layers. And that means that the solar cycle is showing basically the number of sunspots and how these sunspots appear and disappear on the solar surface. And if you plot the number of sunspots, you have all these variations, and they were measured from the 17th century, but only in the 19th century a guy just came to this idea that the cycle is almost periodic. Well, obviously a cycle as every cycle, but you have 11 years, which is the period roughly that the sun goes from lower activity, low sunspots, and upper top of this curve, which is more sunspots. This is a typical active region where you have the sunspot. Just try to compare the area of this sunspot compared to our own planet. You see it's massive, and also you have a lot of different structures in these active regions. So you have a sunspot with umbra, which is the black part. You have the penumbra, which are these filaments like erupting hours from the sunspot. But you also have pores, which are these tiny features here that they only appear like black spots. So basically, for producing these features, you have a complex interplay between the plasma and the magnetic field. And that's the base behind all the activity that you see on the sun. Obviously, it's not as simple as I mentioned before, because you have different scales. So you have large scales, small scales, and depending on the flux, the magnetic flux that it's emerging from the solar interior, you have different features. Sunspots basically are formed because the magnetic field lines emerge, and they cross the photosphere, and they freeze the magnetic plasma. Sorry, they freeze the plasma. And that's why they look darker than the surrounding area, which is much hotter, much brighter. But again, if you go to smaller scales, you have a plethora of activity. So you have small scales everywhere on the sun, and they actually dominate when you have quiet sun. I mean, when you are in the lower part of the solar cycle, you don't have these massive active regions, but you have this lower activity based on these tiny magnetic features. So in this case, you have this large, strong magnetic field, but you also have these tiny, very weak magnetic fields, and they interact everywhere in the sun and all the time at different scales. The whole picture is very complicated, so that's why we still have work to do, and we can specialize in studying, for example, the lower part of the chromosphere or of the upper part of the chromosphere, and you can see how the scales change completely, dramatically. If you go from this, which is very dense, and if you go to the upper part, which is more white and open. But all this is based in observing in multi-waves. So we sort of do tomography of the solar atmosphere and try to compare all what happens on the surface up to the external layers. So we have to develop very nice solar instrumentation. That's another part of the solar physics which I like very much, because you have to be very good at doing observations and know how the instruments behave. So we have space-borne telescopes, we have ground-based telescopes. This image is from a satellite launched in 2010, which is called the Solar Dynamics Observatory. It's from NASA, basically. And you have a tomography of the sun because you have different filters, and they can go from the photosphere up to the corona, and that means that you are tracking different temperatures of the plasma. And the range spans from 5,000 Kelvin till almost 2 million Kelvin. That's all the range covered by the sun. But also you have information of the light that can tell you how the magnetic field is actually behaving on the solar disk. So from these white light images, and if you study the polarization of the light, you can get to these magnetic field images, which are called magnetograms. And if you go to this tiny area here, sorry, I go back, this very tiny area here, which is an active region, you can see how it changes, and actually the sun changes every 10 seconds. In white you have the positive polarity, in black you have the negative polarity, and basically you have polarities going from upwards and then coming down to the solar interior. You also have ground-based telescopes. These are telescopes we are working with. You have data from them. This is a Big Bear Solar Telescope, which is located on a mountain, which is called, and the area is called Big Bear, and that's in Southern California. It's 2,500 meters, so more or less the same as Bogota, but obviously the skies are very clear, and you have a resolution which gives you 37 kilometers on the sun. That's really amazing. It's like trying to see the eyes of a fly which lives in Australia from here. So it's a very high level of resolution. And this is in the middle of a lake, because the water in the lake makes the turbulence less high, and then you can reduce the image motion. And you have a certain amount of instruments that basically take the path of the light, and then you can measure polarization, and you can measure spectrography as well. So now I will show you some very nice videos. So for example, this one is showing the evolution of a sunspot, and you can see how the inner part of the sunspot is not actually dark, but you have a lot of convection also taking place there. So this is called like nanoconvection and nanogranules. So we're trying to understand what's happening here, and you also have these sort of structures which are called light bridges. And these light bridges, they are not only happening on the solar surface, but they actually go up and interact with the upper part of the solar chromosphere, and they generate basically explosive phenomena, which is what we are interested in, because the explosive phenomena on the sun can give you changes in the space weather. This is a close-up of this region. But to generate this sort of movies, you have to pre-process the data, and a big amount of time we have to spend in pre-processing the data and to have these high-quality images with this sort of resolution. But also you can go to different spectral lines, and you can scan the line. If you scan the line, it's like you were doing the tomography of the solar atmosphere. So you go from the lower part to the upper part, and you see how the features here change dramatically. Once again, this one. And obviously, if we stay only with the observations, we don't have the complete picture of the sun. So we have to compare with simulations. These are some simulations of active regions, very well known in our community, made by Matthias Rempel in Germany. And the idea is to compare the one-to-one behavior of the observation and the simulation, and try to trigger and adjust some parameters until we know exactly what's happening here. Obviously, these simulations are made by using magneto-hydrodynamic equations, so it's a complex stuff. Okay, so basically the idea I want to give you today is that we need to observe with different instruments in different scales to complete the whole pictures. And that's what we are doing. We are using data from ground-based, space-based, and we are comparing different layers of the solar atmosphere. That's how we know exactly how the magnetic field is going up and how it's interacting with all the magnetic field that we call ambient field, which is everywhere around. See how the same active region looks in the photosphere, on the photosphere here, and if you go a few thousand kilometers, this is what you see. So it's a completely different picture, and in this one actually you can discover these waves which are emerging from the sunspot. So you have a lot of activity because those waves can also interact with the ambient fields and can generate new features. And once again, it resembles like rain, because actually you have material going inwards again because of the gravity of the sun being 27 times Earth's gravity. And this is one of the most detailed videos of what's happening in what we call a solar flare. So you have all the activity. This is like a tsunami taking place on the surface of the sun. But obviously this is traveling very fast. This is supersonic velocities here. But now let me tell you also that it's not only active regions. We also analyze small regions of the sun, which are called granules and convective motions. We also do observations with different instruments. So we have space-based instruments and we have ground-based instruments here. And this is one region we analyzed recently, where you have this area where you can see the granules, but the granules evolve and they track the magnetic field. So you can see these sort of structures here, which are called jets, and those jets are also injecting energy into the upper layers of the sun. And this is trying to solve a mystery, which is actually one of the problems in solar physics, and is trying to understand why the solar corona is hotter than the solar surface. So if you go from the solar surface, which is 5,000 degrees, to the upper corona, which is 2 million degrees, then you have this big difference of millions of degrees, and we don't know exactly why this is happening, because you are supposed to reduce the temperature if you go outwards from the source of energy, which is the center of the sun. So basically, we sort of discovered that the emerging flux interacts with the ambient fields, and these sort of explosions are injecting energy into the upper layers. Okay, so this is basically what we do, is try to mask these areas and plot these curved lights and see how they variate. Future work, we are still working in these small features, because we know, the community knows, that if the sun is in the minimum, you still have this coronal heating problem. So it's not only exclusive when you have active sun, but also when the sun is quiet, you have these big changes in temperature. You have also this very nice satellite, which was launched in 2006. But if you want to compare, this is the satellite image, and this is the ground-based image. So this is like, wow, you observing from the ground, even though we have the atmosphere, you can get very nice images, obviously in periods of time which are shorter than the ones you have in the space, which is 24 hours. If you go to space, you have this 24-hour observation, and then you can obviously get a very nice picture of what is happening all the time at different parts of the sun. This is the Solar Dynamics Observatory I already mentioned, and coming soon we have more instruments. Dr. Shapiro mentioned some of them, but we have which is going to be the largest solar telescope in the world. It's being built in Hawaii, Mauna Loa Mount, and this is going to be 4-meter aperture telescope. First light will be in 2 months' time. Actually, my ex-supervisor is the one who is directing the construction of this telescope. And we have the Solar Orbiter mission, which is going very close to the sun, but is going out of the ecliptic. So for the very first time, we will gonna see the poles, probably the very top part of the sun, which is very interesting because we don't know exactly how it's behaving. We always look at the line of sight of the sun, I mean the solar disk. But also, last but not least, we have in Colombia the idea of having a solar telescope, not the best one because we don't have a very nice sky. We only have in Bogota like 30 clear days in the year, but still we have some chances to observe for 1 or 2 hours, and this is a project we are working with people from Germany, but also England and the US. We want to install this binocular telescope, and we want to observe the sun in low resolution and try to infer the variations in the magnetic field on the solar surface and apply a technique which was developed by the University of Sheffield, in which analyzing the variation in magnetic field, you can infer when a solar flare is going to happen with at least 15 hours in advance. So that's our next project for the next 3 years probably. And that's all I wanted to say. Thank you very much.